my screen. And then start here. Okay, so yeah, here we go. So the background of this whole thing dates back to sort of the 1990s, when I was a grad student and learned about how people determine parameters in models. And ultimately, this all comes back to the fact that what we want to do in applied and computational math is to simulate the world around us. We want to predict things, right? We want to predict how air flows around an airplane so that we can design it in a better way, for example, or we want to figure out how much does a bridge deform as you drive a truck over it, and maybe you want to use that information to determine what kind of I-beam or what thickness of steel you need to build that bridge. You want to predict the weather. I picked that example because I want to go into the mountains on Saturday, and the weather forecast is so-so. So I would love it if there was a better forecast for this. And then, of course, I'm looking out onto the foothills here, and for several weeks I've had heavy smog from there, heavy smoke. So things that you would want to simulate in that case would, for example, be how does a fire progress if there's wind. So for all of these sort of things, fundamentally, what we do in applied and computational math is to build the tools to do this. And so if you do want to do this, you need two pieces of information. One is a model. The model says, you know, there's a balance of forces and they all balance out. So let's say if you drive a truck on the bridge and you stop it there, there's going to be a force, gravity force from that truck onto the bridge, and there's going to be a reverse force in the opposite direction that comes from the internal stresses in the elastic material. So there's fundamentally something like Newton's law, that mass times acceleration is the sum of external forces, and if you're in a steady state, then Newton's law says that the sum of external forces must be equal to 0, and elasticity, the science of how bodies deform, is fundamentally just that the sum of external forces must be 0. So the model is one thing that describes every object of this kind. And so it's generic. It describes every elastic body, or it describes every fluid flowing around an airfoil, whether that is gas at certain density or whether that is, I don't know, helium or water. Fundamentally the same idea, right? The other part that you need to know is parameters that appear in this model. So when you want to simulate air flowing around an airfoil, you need to know about the viscosity of the air and the density too. If you want to simulate how a bridge deforms, you need to know something about the stiffness of this material. So you need to know that it's made from concrete or from steel or from wood or whatever it is. So there's a parameter in the model that describes the specifics of the material that it's built from. And for wildfires, for example, you would want to know a parameter that could describe, for example, how fast the fire front progresses as a function of the wind speed. There's going to be another parameter in there that determines how hot the fire burns in response to what kind of fuel you have, and so on and so forth. So these are specifics about the situation that you want to deal with, whereas the model is generic about the situation. So to give you a simple example that everybody can relate to, because we all had that in our high school mechanics courses. So if you took a spring, for example, then you could ask the question, how much would it elongate or compress if we apply a known force? So if I apply a force of 10 newtons that expands it, how much longer would that spring become? So what we all learned is that delta x, this elongation, is equals to F over d. F is the applied force, and d is what we call the spring constant. So the model is universally true for all springs of this kind, within limits, of course. I mean, let's say for small deformations. So the model is universal. The parameter d, that depends very much on what spring you have. So that looks like a pretty sturdy spring in this picture. So d is probably going to be fairly large. You need to apply a large force to obtain a moderate displacement. But if the thing had been made not of a thick steel rod that has been bent, but chicken wire, then d would be fairly small. So the model is universally true. The parameter is specific to the situation here. And so if you knew what the inputs, that's the F is, that's the external forces that you apply, and you knew what the parameters are, this d, then you could predict what this delta x is. That's what we call the forward problem. So the forward problem is given the specifics of the model and its parameters and the inputs, predict what the outputs would be. So, but of course, in order to do these forward simulations, to predict what comes out, you would need to know what these parameters are. And the challenge conceptually, and this is now a philosophical question I'm going to address, if you want to know what these parameters are, you need to measure them somehow. And it is a realization that I had a few years ago when somebody was talking about this, that there's really only two things that you can measure. It's length and it's time duration. And time durations really is just you're counting clock ticks, for example. So everything else cannot be measured. You can measure derived quantities. So if you, for example, wanted to measure a weight, you would put it on a scale. The scale would go down and it would rotate an arm on a dial. Well, what you're doing really is it measuring a length, right? How much did that dial move over? If you want to measure a voltage, fundamentally, you measure a length on a dial. If you measure a voltage with a digital voltmeter, then what you really do is you count. There's a comparison internally, splits the voltage in multiples of, let's say, 1 volt, for example, and you count how many times up do you need to increase the voltage until you hit the one that you want to measure. So
Wolfgang,
the only things you really can do is measure length and time durations and clicks. So count.
Wolfgang?
Yeah?
Would you permit, just so that I can understand this, I mean, I could also imagine like an interferometer where I just measure whether there's interference or not. It's purely on off. There's not really a length there. It's just whether the signals cancel.
Yeah, you count in that case.
So would you classify that as time or as length, or does it matter?
I should have written this differently. When I say time durations, what I mean is I count clock ticks.
Okay, thanks.
So the only thing that I can do is measure length and count. And that really boggled my mind when I learned this the first time. And I mean, I keep thinking that maybe I'm actually wrong about this. But I think it is actually true that fundamentally every device in the analog era, at least, that I can think about, really just, it has a dial, so you measure length, or it counts. That's all there is. So if you wanted to measure something like this spring constant d, you can't measure d itself. All you can do is you can measure related quantities, and then you need to use an interference process. So there's an epistemological question. What do I actually know, right? How do I determine the things that I want to know? So the approach to determine coefficients or parameters in models, that is called an inverse problem or a parameter estimation problem. Inverse problems are sort of parameter estimation problems in a very specific context. But so it's the inverse to the forward problem. Namely, if I knew the parameters and the inputs, I could predict the outputs. That's the forward problem. And the inverse problem is, if I know what the inputs are and I have measured the outputs, then I can ask the question, what kind of parameter would have yielded these outputs so that my prediction is as close as possible to what I actually measured, right? So the inverse problem is determine the parameters by comparing predictions with actual measurements. So in the case of the spring, for example, what I could do is I could measure the elongation for a given input. So in that case, I know f, and I know delta x, and I ask what kind of d would have produced this delta x. So I would like to find d, the spring constant, so that the difference between my measurements and the predictions are related to d in this way here, becomes minimal. And if I have only one measurement, so I apply only one force, I measure delta x only once, then it's pretty obvious. So I know what this f is. I've measured this. Then d must be equal to f over delta x measured. But I could do this kind of measurement many times, right? So for different input forces, I get different measured delta x's. And in this case, this would be a whole vector of measurement values. And this here would be a whole vector of predicted values for different forces, but the same d. And in that case, I can't solve for d directly, but I can ask the question, what d would minimize the difference between these two vectors in some norm, for example. So that's conceptually what an inverse problem is. That I have a model that can predict, and then I ask the question, what coefficient, what parameter in this model would best predict the values that I actually measured? So this example is just too simple. So I'm going to come back to something that Danny Long, one of my grad students, showed last week. And for those of you who were there, maybe you recognize some of this. So the idea, he's working with a bunch of folks over from chemistry under the direction of Rick Finke. I should have also said Patrick Shipman is also involved in this project. So I'm drawing on what all of they have already done. This picture is from Wikipedia, but it illustrates the general idea. So nanoparticles are sort of agglomerations of, let's say, platinum, or I think in this case it's hafnium atoms that form small particles of maybe a few hundred, a few thousand, a few 10,000 atoms. And there's a process by which you can grow them, the chemical reaction. And one of the things that people want to understand, but don't really, is how do these nanoparticles grow over time? And what is behind an empirical observation that the size distribution of these particles is actually quite uniform? So you start out with just individual atoms as part of molecules in a solution, but think about it as individual atoms, and then you wait with this reaction for an hour, for example, and you end up with something like this, where roughly speaking, all of these nanoparticles have more or less the same size. And it's maybe interesting to understand what the processes behind this are, but ultimately what we would like to do is predict the size distribution because we want to control it. And you have an application for nanoparticles in mind. It says you need nanoparticles of size 50 nanometers, for example. Well, how do I have to run my chemical reaction in such a way that I get nanoparticles of exactly 50 nanometers? So in this picture here, let's say 14 nanometers. Where I have a different application in mind, how do I need to drive my conditions in such a way that I get a different size for these nanoparticles? So these are typical things that I would like to simulate on a computer, because doing experiments by and large is much more expensive than doing computer simulations. And in order to do this, I need to come up with a model. In that model, there will be parameters whose values I generally don't know. And so then I need to determine these coefficients. So the forward problem would be, if I know these coefficients, I can predict particle size. And the inverse problem would be, I don't know these parameters, but I have measured particle sizes, and I ask the question, what parameters would best predict the particle size distribution that I observed, that I measured? So in this case, the model is a model that Rick Finke's group has developed that consists of on the order of 2,500 coupled ordinary differential equations. So this model of sizable complexity, right? It's not as simple as delta x equals f over d, but a collection of 2,500 ODEs in which these 5 coefficients somehow appear, kb, k1, 2, 3, and m. And what they all mean is maybe not terribly important. So forward problem is predict particle sizes. The inverse problem is determine these parameters. So I would like to find parameters in such a way that the difference between my measured and my predicted particle size distribution, PSD is the particle size distribution, that the difference between these two is minimum. So the predicted ones, that is the output of my model given certain parameters. So here's how one, the predominant, the old style paradigm of inverse problems can then be posed, right? So I have parameters, I have a model, I have known inputs, I have measured outputs, and I want to find a single set of parameters that I'm going to call K1 star, K2 star to Km star. So that's this difference between measured and predicted outputs is minimum. So there's hopefully exactly one set of such parameters. Maybe sometimes there are more. So maybe this function here, this sort of thing here could have multiple minima, for example. Let's pretend at least for the moment that there's only one. And then I would like to find those parameters that minimize this difference. That is what we call the deterministic inverse problem. The term will become understandable when I show you what the stochastic or the Bayesian inverse problem is in a minute. So this is a different perspective that you could have on this. So I told you before that the spring has a constant d. Right. So when I went back, the way I was thinking about this is this spring has exactly one spring constant d. It's one spring, it has one spring constant. And a different spring would have a different spring constant, which I could also measure, but it is one object that has only one spring constant. And people, I don't know, quite a long time ago, decades ago, realized that maybe that is not the best perspective on this. The reason for this perspective comes from the following observation. So what I really measured, this measured output here, is not really a number. So if you think, or any set of measurements. So if you think about this from the perspective of the spring, then we should probably realize that even if I apply the same force multiple times, and I measure multiple times, I'm not going to get exactly the same value. What I'm going to do is I take my spring, I apply a force that elongates, and I put my ruler next to it, and I'm going to measure how many millimeters did the spring elongate. And so the first thing to note is that, well, I'm probably not going to be able to measure the exact elongation anyway. I'm going to be able to measure this to maybe a millimeter of accuracy, okay? But then if I do this experiment multiple times, I probably also can't apply the force in exactly the same way every time. I mean, I don't know. I'm going to hang it from the ceiling and I'm going to attach a pound weight to it. But maybe sometimes, I don't know, there's this much of finger grease on it. Or maybe the humidity is different and so it weighs a little bit more. So the way I should think about this is that this measured output is in reality a stochastic quantity. There is no exact measured output. There is a probability distribution of measured outputs. If I were to repeat the same experiment many times over, I would get a probability distribution for these measured outputs. For each one possible measured output, I would get a best fit set of parameters. Okay, the one that minimizes the difference between the prediction and the measurement. But because the measurements are not always the same, the identified parameters should also not be the same. So the way I ought to be thinking about these sort of issues is not so much as find one set of parameters that fit the measurements best, but that I should think about there being a probability distribution in parameter space that describes how likely it is that a set of parameters is in fact the physically correct one. So that's,
Wolfgang,
yes?
is there permission to have dependence between these, or are these independent?
You mean the K1s to Km?
Yeah. So I can imagine you using the same spring over time. Maybe it gets weaker or it gets hot, who knows? I'm just saying, like, you can imagine many physical situations, you can't reproduce it without dependence between the measurements.
Yeah, well, and I will have to figure this out somehow, right? So one way I can do this, for example, is that I measure multiple aspects of this. So the spring is maybe not the best example, but if I take other devices that measure multiple things at the same time, so I could think about so if you elongate the spring, it's going to shrink in radial direction, right? I mean, if you stretch it in this direction, it's going to shrink in the other direction. So maybe in addition to measuring the elongation, I'm also measuring the shrinkage. So both the elongation and the shrinkage are stochastic variables, but they're not uncorrelated, right? So if for whatever reason it's hotter, the spring is a little bit weaker, it's going to elongate more, it's going to shrink more, right? So these the probability distribution on the measured outputs is going to be correlated on the individual components of my measured output vector. And as a consequence, you bet that the probability distribution on these Ks is also correlated. As a matter of fact, I'm going to show you this in an example later on. So I am looking for a probability distribution on all of these, K1 through Km, and not a probability distribution for the K1s and a probability distribution for the K2s and for the Km separately.
Thanks.
Does that answer the question?
Yeah, I think if it doesn't, I'll keep watching and see if my question gets more clear.
Okay. So the way you should think about this probability distribution that I seek, right? So it is a probability distribution on the space of these parameters K, given that I measure something. So the way you should think about this is how likely is it that a particular set of parameters is correct, given that we know the measured output. So I'm going to get something of the following kind. So if the output comes back the same every time, then there is likely going to be a delta. This P here is going to be a delta function. Okay, but if these outputs are widely distributed, if I get different values every time, then this P is going to be a probability distribution that also allows for multiple K, for multiple sets of K parameters to be more or less equally likely, or maybe there's sort of a maximum somewhere, but many different Ks are likely to produce the thing that we measured. That's sort of how you should think about this. So my goal then in this Bayesian inverse problem, in the stochastic inverse problem, is not anymore to find one set of parameters, but to find a probability distribution on the parameters. Okay, and so the question is, how do you do this? And that goes back to Thomas Bayes. So we call this a Bayesian inverse problem. It's based on Bayes' theorem from 1763, which I'm sure he would have appreciated to see in action, but he actually died 2 years before it was published, and it's not quite clear whether he actually wrote it or whether just somebody else wrote the theorem based on some verbiage that he had provided at the time. But we attribute it to Bayes like we attribute a lot of things to people who had actually very little to do with it. What I'm interested in is a probability distribution on these parameters given the output. That's the object I would like to know. And Bayes tells us that this probability distribution here is proportional, so up to a constant equal to the probability of getting the measured output given a set of parameters times some prior knowledge on these coefficients. So maybe I know, for example, that all of these p's, all of these k's are positive numbers or need to be positive numbers, in which case this p is a distribution that would be 0 if any of the k's is negative and 1 if they're positive. So the point is that this is the thing that I want to know. This is something that I plug in, that's my prior belief, and this thing here, well, that is something that I can compute, right? So it is so basically what this is the likelihood of getting a measured output given that I know these parameters. That's my forward model, or there's my forward model in there somewhere, right? Namely, I take all of these parameters here and I predict what I would see, right? So I get an output predicted, and then I would ask the question, okay, so if I predict 2.75837, what is the probability that I actually measured 2.75 or 2.76? Okay, that's just a statistical problem. I mean, I need to know something about my measurement device, but fundamentally, I take the case, I predict an exact value that I would hope to see. How likely is it, given this exact value, that I actually measure output measured? So this thing here is something that I can compute at the cost of evaluating my forward model. So so I had the question, how likely is it that K is correct given the output? Okay, that's a question that's difficult to answer. That's the inverse problem. That's a question of attaining knowledge. Here, I've played this back to the following question, namely, how likely is it to measure the output given that these Ks are given? Right, so that's this problem here, and that's a computable thing. This is something I can do. So what I really want is this, and I compute it by this product here. And just to give you an example of what Danny has already done. So Danny did this for his model with the data that we have from the Finke group. So he computes then probability distributions on this 5-dimensional space of parameters. And then he computes marginal probabilities. So for example, if he just looks at one of these coefficients, he gets a probability distribution that looks like this. And if he looks at 2 of these parameters, then the marginal distribution of this 5-dimensional function in the 2-dimensional space would look like what he has at the bottom right. So that's sort of the idea, right? That I would like to get information about how likely certain parameters are. And so, for example, what we can conclude from something like this is that the particle size cutoff is probably either about 400 or about 1300, and with slightly lower probability, maybe 1200. So that's sort of the way we would like to interpret this. So there is no single best particle size cutoff that best predicts all of the data that we have, but these probability distributions can look complicated. That's just how they are. So the output of this whole thing is a probability distribution that is in general a function of many variables, and in general also a complicated, complex function for which I do not have an analytic formula. Right? So if you ask me, well, what is the mean value of this distribution, or what is the mean value of this distribution? That's not so easy to say, right? I mean, I cannot easily compute this without actually forming the integral. So the integral, the mean value of a probability distribution p of x is integral x p of x dx. And so I need to compute these integrals, for example, to tell you something about this. So the important part really is that this Bayes formula here, it gives me a way to compute this. right? So if you give me, if you ask, what is the value of p for a given set of k's, then I can compute this through this process over here on the right. But fundamentally, that by itself does not help me much. I can plot these sort of curves if I wanted to, but I still don't really know all that much. And if I'm in 5-dimensional space or later on in 64-dimensional space, things become a lot more complicated if you have a function of many variables for which you don't have an analytic formula. So what I need to do is I need to be able to somehow not just evaluate this p for a given set of parameters, but I want to statistically characterize this. I want to ask the question, well, given this thing here, for example, what is the most likely set of parameters? Well, that would be somewhere here, right? So this k1 would be, I don't know, about 1, and the particle size cutoff would be maybe 1400, okay? What is the mean value? Well, that's probably going to be a point somewhere here. What is the standard deviation for this particle size cutoff? Well, it's, I don't know, maybe 600. Looking at this, seems about reasonable. Right, so I would like to have some way to assess the statistical properties of this probability distribution. And I do this typically on a piece of paper by writing down integrals, right? So the mean value would be integral x p of x dx. The standard deviation would be the integral of x minus x bar squared p of x dx, x bar being the mean value, right? So all of these are integrals, and if any of you have taken, a course in essential numerical analysis, you know that computing high-dimensional integrals is actually really, really complicated. We can't do that. So if I give you a function of five arguments, so it lives in 5-dimensional space, to just compute the integral under this function, so the volume under this function in 5-dimensional space is not feasible. So the way we do this, things like compute the mean value standard deviation of this. The way we do this is that we replace all of these integrals with sampling. So what we would like to do fundamentally is come up with a sequence of 5-dimensional vectors for these 5 parameters k, so that the density of samples in the sequence, so if I visualize this as points in 5-dimensional space, what I would like to achieve is that the density of these points in 5-dimensional space in the limit of infinitely many samples becomes equal to the probability given to a certain volume in this 5-dimensional space. So that's sort of the idea, that I need to come up with samples so that in those places where p is large, I end up with lots of samples. And in those places where p is small, I end up with few samples. So if you had just the Gaussian, for example, in 1D, you would have to have a lot of samples in around the zero, and fewer samples the further you go out. So the typical algorithm to do this is called a Metropolis, a Markov chain, a Monte Carlo Markov chain, an MCMC algorithm. And the one that everybody uses is called the Metropolis Hastings sampler. Originates in the early 1950s, and again, it is not quite clear what exactly the role of Metropolis and Hastings are. There are numerous other people who also have claims that they invented it in that same group. So again, an example where attribution may or may not be accurate. So the algorithm works fundamentally like this. I start with a point in my 5-dimensional space, and then I propose a nearby trial sample. Then at that sample, I have to evaluate, so at that sample k nu, and that's my 5-dimensional vector, I have to evaluate my probability distribution. Okay, and I do this through Bayes formula by doing one forward simulation and comparing with the prediction based on K nu, how that compares with the actual measurement. So I can compute this probability distribution here, and I can compare that with the old probability distribution at the point where I currently am in my sequence of points in 5-dimensional space. And based on some criterion that's maybe not terribly important right now, I either accept or reject this new sample. If I accept it, that's where I go, and I start this process again. I pick myself a trial sample somewhere in the vicinity, and I repeat. If I reject it, I just stay where I am. So I'm going to get a sequence of points in my 5-dimensional space. And if I make this acceptance decision, if I do this right, then the density of these points will correspond to the size of P. So what I get is what's called a Markov chain. So a Markov chain is just a fancy name for a sequence of points where each point's location is computed based on the previous one. So there's a random process involved in this, but the location of the nth sample depends on where the previous one was. So I compute this one after the other, after the other, after the other. And for each sample that I compute from this chain, I need to solve my forward problem once. So Metropolis Hastings is sort of the simplest one. There are many, many variations of this fundamental idea. They're all not terribly important, but the key piece that is important is that in high-dimensional spaces, I need many, many samples. So if you think about this, I can probably characterize a one-dimensional Gaussian where the mean value is and what the standard deviation is with maybe just 100 or 200 points. But if I have a two-dimensional Gaussian, I'm probably also already going to need 100 squared points, so 10,000 points. And if I go to higher and higher dimensions, I need more and more and more samples to get an adequate representation of my function. So in high-dimensional spaces, I need many, many samples. And the accept and reject decision requires me to evaluate the model every time. And the model is not too expensive if it looks like delta x equals f over d. But if you take Danny's plots that he showed last week, and so this one here, for example, so he computed about 1 million samples in his chains, and the forward model that he needed to evaluate every time takes about 40 seconds of compute time, if I remember this correctly. So if you multiply this out, he burned about a CPU year for this. He didn't wait for a year. You can't write PhD thesis if you need to wait for a year for each graph. He just used a few, well, I don't know, a couple hundred processor cores to do this. But so you get the idea that these sort of computations are actually really expensive. And so the fundamental question that we really need to figure out as a community of people who want to do these sort of computations is we need better sampling strategies than simple Metropolis Hastings. We need a way where we don't need 1 million samples, but where maybe with just 10,000 samples, we can get the same amount of information. So that's sort of the motivation for what I'm going to talk about for the next 10, maybe at most 13 minutes, that's how much I still have, that we need better sampling strategies. And in order to do this, we need to be able to compare different sample strategies, different samplers. And the way you compare them is typically on a benchmark problem. So a benchmark problem would be that there is a probability distribution that you want to sample, for which you know the mean value in the covariance matrix, for example. And you ask the question, okay, for algorithm A, how many samples do I need to get the mean value correct to 1% accuracy? How many samples do I need to get the covariance matrix correct to about 1% of accuracy? So that's sort of the idea. I want better sampling strategy so Danny does not have to run a 1 million samples that cost him a CPU year. And the example that I'm going to show you in the following is something that I've been working on with David Aristoff. So he's been helping me with a lot of the statistical interpretation. I'm not so much a statistician, So he has a lot more experience in this than I do, and points out all of the mistakes that I make. And then there's two other people that I want to acknowledge. Dawson Eliason, an undergraduate student I work with, and Mantatas Rimkus, who was a stat grad student who did some of the work too. So this, both of them work on the software implementation of these sort of things. So here's the benchmark that I want to use to compare different sampling strategies. I'm thinking of not a string, but a membrane. The membrane is composed of 8x8 patches of material of unknown stiffness. So there are 64 parameters in there. That's the stiffness of these patches. I subject this to a known force, and then I measure the deformation at 169 points. So if you look at this picture down here, so you think of this as a membrane that is clamped on the boundary, so it's, say, attached to a frame. You apply a force from the bottom and you push it up, and you measure how it deforms. And you get the idea that there's an area where this membrane is particularly stiff, so it doesn't deform very much. And there's an area where this membrane is particularly soft, and so it bulges out. So if you think about it as a membrane made from rubber, there's a patch in here where the rubber is particularly thick, and here where the rubber is particularly thin, so that I get this sort of deformation pattern from the force that I apply. So what I want to do is I apply a known force, I measure the deformation at these 169 points, and I would like to identify what are the parameters that would have predicted this sort of deformation. And not just what are the best parameters, but what is the probability distribution in the 64-dimensional parameter space that predicts this. And so we can do this, right? So I can measure these things. I can define my probability distribution on these 64 parameters. So if I do this, if I run this whole procedure that I outlined, what I'm going to get is a picture like this. So this is, for each one of the 64 patches of this membrane, what's the best predicted or the mean value for each one of these parameters are. So there's these four over here that have, so this is the stiffness of this material. So they are particularly stiff. You see that these four patches have a high stiffness. These four patches here have a low stiffness, and then there's sort of, well, average values in between. Okay, so these seem to be the kind of parameters that would have predicted this deformation. So I can do this with the mean values. I can look at them for these 64 parameters. I can look at what are their values that I expect. Okay, so the red dots here indicate the size of the stiffness for each one of these 64 patches. There's some spread here, so I run the same kind of experiment multiple times. So I'm going to get a probability distribution for the correct value of these stiffness coefficients, and you see that some of these I know pretty well. These ones here, these ones over here, some I don't know so well. And so for some of these, I know several digits of the parameter. For others, maybe a digit and a half. But then I told you that I'm not so interested in actually just figuring out what is the most likely parameter, but I'm interested in figuring out what the distribution of these parameters are. And so here you see the probability distribution for all 64 of these parameters. And you see that some are pretty nicely peaked. So let's say these two parameters here, they have a value around 0.1, and they're with, I don't know, 95% probability they're between here and here, for example. So I know them pretty well. But then there's other parameters here where the most likely value is here, maybe 3 or so, but they have very long tails. And so I can actually characterize this parameter distribution by looking at these probability distributions. Okay. I can also ask about correlations. So for example, what I show here is a marginal distribution for the 45th and the 46th of these parameters. And what see is that they form sort of ridges. That means that if the 45th parameter is large, then the 46th is likely small. And similarly, if the 46th one is large, so I'm over here, then the 45th one is probably small. And I mean, there are ways in which I can explain why this is so. I think as a mechanical system, it's not very hard to explain this, but that's sort of the idea. And so I can compute these correlations. I can also do this in terms of the eigenvalues of the covariance matrix. So the covariance matrix is often a good tool to figure out how correlated these different parameters are. And so you see that so the large eigenvalues typically mean that there are coefficients that I can identify well, or combinations of coefficients that I can identify well. And then there's a whole bunch of small ones that tell me that there's also things that I cannot identify well. So that is another way of seeing this. How do I compute this? So I implemented a fairly simple Metropolis-Hastings algorithm because I wanted to use the simplest algorithm as a baseline. That is not an efficient way of doing it. But I wanted to use it because this way allows me to characterize the statistics of this probability distribution without having to worry too much that I have a complicated algorithm that may not be correct for this particular problem. What I do is I run these Metropolis-Hastings chains where I compute each sample one after the other. Each sample in this case is a 64-dimensional vector. It's a point in 64-dimensional space. And each chain has 10 to the 8 samples. And so I end up with 10 to the 8 points in my 64-dimensional space. I worked a very long time at making this code fast. So when Danny's code takes 40 seconds, my code actually only takes 5 milliseconds per simulation of a membrane. And that's because I used all sorts of information that's specific to this particular problem. But if I put this together, 10 to the 8 samples, 100 million samples that each take 5 milliseconds, I still end up with 6 CPU days per chain. And I ran about 1,500 of these chains. So I have now on the order of 150 billion samples. That took 25 CPU years to compute, and it takes about 12 terabytes to store. So these are really, really expensive computations. I can look at this, how this looks like. So for one of these chains, this is, for example, the first component and the second and the third and the fourth and the fifth component of these 64-dimensional vectors, and you see how they oscillate around. But so this one seems to be stuck at around 0.1. So the mean value of this is going to be around 0.1. So this is how one of these chains looks like, or let's say the first 100,000 samples of this. I can also look at how these chains converge. And so what I'm asking is, can you compute the mean value of these 10 to the 11 samples? So that's the mean value in my 64-dimensional space. And of course, if I only consider the first million samples, for example, then the mean value of the first million samples is going to be different from the mean value of all of the samples. And so what I would hope is that if I take more and more and more samples and take the mean value, they will all converge. And I can show this here. So each one of these blue curves corresponds to one chain. And you see that the error, so the distance between the mean value up to a certain number of samples converges to 0. Or let's say the distance of the mean value up to a certain number of samples, the distance from that point to the true mean value of all of the samples converges to 0. So that's one way how I can measure how fast my algorithm converges. That if I throw more and more and more samples at it, I get more and more and more accuracy. Okay, but you see that this is the relative error here. That even after 100 million samples, I have a relative error for each one of these chains that's still only on the order of 1. So it's very expensive to compute these sort of statistics accurately. There's one reason for this. So I'm might have 10 to the 11 samples, but these chains move slowly. And so if you think about if you wanted to sample a multidimensional Gaussian, and from each sample to the next, you only move a little bit, then they're highly correlated. You really actually need a lot of samples to get around this whole probability distribution once. And so in reality, for example, I have in this example here only about 10 to the 7 statistically independent samples. So if you think about in 64-dimensional space, if I had only 2 samples in each coordinate direction, then I would need 2 to the 64 samples to just form the corners of a cube. Well, 2 to the 64 is about 4 billion. So I have only on the order of 1/200th of as many samples as I would need to have just 2 statistically independent samples per coordinate direction. So you get the idea how expensive it is to compute good statistics. And so I'm getting to the end here now. What can I do with such a benchmark? So first, it's a benchmark that is reminiscent of a lot of things that we want to do in this community, namely identify coefficients or parameters in partial differential equations. And in this case, the partial differential equation is the one that describes how a membrane deforms. So it's a benchmark that is relevant to the community. It's clearly challenging. If I needed 25 CPU years to give you a couple digits of accuracy, then it's clearly challenging, but I have fairly good statistics now. So I have a pretty good guess of what the correct answer is. And what I can do now with these correct answers is that I run other sampling methods, right? So instead of a simple Metropolis Hastings, maybe I can use, I don't know, a delayed rejection adaptive metropolis on a multi-level hierarchy of probability distributions. And I can test how many samples does this algorithm need to give the same accuracy as the one that I've computed with my 10 to the 11 samples. And if that algorithm only needs 10 to the 9 samples, well, I can make a case that this is a much better algorithm that I can actually use for real applications, right? So the point is that I want to have a benchmark for which I have good enough answers, but that's also relevant to the community as opposed to simply being, sampling from a multidimensional Gaussian, for example, which is not representative of the problems that we really want to solve. So the ultimate goal is to use all of this for real inverse problems, let's say in biomedical imaging, in oil reservoir properties, in what we know about the Earth interior, these sort of things. And so just to sum this up, so Bayesian inversion is a different approach to asking what is the value of this parameter. It doesn't give me just a single value, but it gives me a probability distribution for this. So it's a much more powerful conceptual tool to think about the parameters in my model. But it is, of course, very, very expensive. And if I wanted to use this for real applications, I need a much better algorithm to sample. And I think that's where I leave it. The point of this benchmark that I showed you in the second half is that I can evaluate and compare algorithms. And that's what I look forward to doing with David and my other collaborators, that we now that we have the answers, we play with different sampling algorithms. So with that, I'll stop. Thank you.
Okay, thank you, Wolfgang. Now it's time for questions. Any questions? So I have one. So so by this estimation, you should assume that there's a defined form of distribution, assume it's Gaussian, and then we try to approximate the parameters in that Gaussian, for example. In your case, because I saw for your problem, you have the distribution of your partner, for example, the nanoparticle size is, they have multiple peaks, which of course that's not Gaussian. So my question is, are you still assuming that particular form of the distribution, or it's totally arbitrary?
No, I make no assumptions. I'm saying here's my forward model. These are the parameters that I would like to identify. Compute the probability distribution for these parameters, and whether that is a Gaussian or not. plays no role in the algorithm. So, I mean, if I knew that the probability distribution on these parameters is Gaussian, there are much more efficient ways of computing the parameters in this Gaussian. So in that case, all I would need to do is compute the mean value and the covariance matrix, for example. I can do this, I don't know, at 0.01% of the cost, as I have done for my benchmark. But that lives on the assumption that the distribution for these parameters is Gaussian, which in reality they almost never are, right? So the Bayesian approach specifically does not make that assumption and says, compute it. Compute what this P of K is, and then we can look at it and we can think about whether it is Gaussian or almost Gaussian or not Gaussian at all.
So what is your result for your problem? Did you find that's close to Gaussian, or we have multiple Gaussian or something like that? Because I saw that in many cases, and if it's not single Gaussian and we can put multiple Gaussian there, and we can still get quite reasonable, quite well approximation for most of the problem.
Sometimes, but not always. So let me give you an example. So if you know that the Earth's interior is can be seen as a liquid on very long timescales. It's solid rock, but it behaves like a liquid. And I can ask the question, for example, what is the viscosity of this liquid? I mean, more than 100 years ago, people had the first estimates that it is 10 to the 24 Pascal seconds. But today we know that it varies between 10 to the 18 and 10 to the 26, for example. So is it Gaussian? No, almost certainly not. So maybe the logarithm of this thing is Gaussian, but it's definitely not Gaussian itself, because the Gaussian probability distribution for the viscosity would have non-zero probabilities for negative viscosities, which clearly does not make any sense. Okay. Maybe the logarithm would be Gaussian, but it still isn't. I mean, if you look at the viscosity of different parts of the Earth, you will find that the probability distribution is not, in fact, Gaussian. And I think there are many processes where the output probability is not Gaussian, and to make the assumption that it is going to deprive you of a lot of insight. If all you compute is the mean value and the standard deviation of the probability distribution because you assume that it's Gaussian, then you might learn very little. So, I mean, let me go back to this slide here, the one that Danny had produced. So, if you look at this probability distribution, so it's clearly very expensive to compute this. Okay, if I had made the assumption that it's Gaussian, then all I would have computed is the mean value and the standard deviation. And so I would have, in essence, said, I can approximate this one here by a Gaussian distribution that somehow sits in here. That makes no sense, right? I mean, that's a terrible approximation. But you would never know if you didn't compute the probability distribution. So I mean, I should also say, I'm not 100% sure that this is actually correct. It's quite possible that this is a slide that I had from Danny from a time when he didn't have enough samples yet, and that with more samples, this actually turned out to look very different. But you get the idea, right? That the assumption of Gaussianity deprives you of a lot of information that you can get if you assume that you need to compute the whole probability distribution.
Yeah, fair. Thanks. Other questions?
I just had a comment because you said when you first heard someone say that all you can do is sort of measure length or time, it reminds me of another similar comment I once heard someone say. It was at a P-adic and ultrametric analysis conference, and someone started by saying, all we can measure are rational things. So why would we assume we can fill in what the gaps really are?
Yeah, I think that's an excellent example too, right? I mean, your model might predict an elongation of square root of 2, but you will only ever measure 1.4 millimeters or 1.5 millimeters, right? Nothing in between. So rationals might even be an overstatement. It's actually a very small subset of the rationals. You could think about this as a fairly small ball, actually, in the integer lattice of enumerator and denominator, right? We're not measuring things to 16 digits of accuracy.
I'm not sure this matters, but I sort of think, to play devil's advocate, you could have a unit circle, and now you have an irrational circumference that you're able to measure very accurately.
But how are you going to measure it?
Well, you just simply know it's a unit circle, and so therefore it has an irrational circumference, and anything you compare it to is an irrational length, but you created it in a very simple, direct unit measurement.
Okay, but you compare it to something else. So you
Absolutely. I'm not saying it doesn't give you more computational power because it's still from a finite set of operations, but the actual number of square root of 2, I could build on a triangle. Yeah. With ruler and compass, I have such an irrational. So I don't quite buy the premise that we don't see numbers outside of the rationals.
I think where Emily was going with this is that if you put a ruler to a dial, or if you have a dial that shows you something, right? Of course, that dial itself conceptually can be in any position, right? But you're not ever going to measure square root of 2. You're going to read your dial on a millimeter by millimeter scale, for example, and you're going to either call it 1.4 or 1.5, but not square root of 2.
Yeah, I mean, I'm not trying to be right, but I think I could measure the size of a football field and determine I have a measurement that's irrational. I can have external data giving evidence of things that I can't measure precisely myself, but I can measure other aspects that convince me of this irrationality. That's all I'm trying to say.
Fair enough.
Other questions?
I had a sort of boring question. I didn't catch the argument about having 2 samples per coordinate direction.
So think about if you're in a 2-dimensional space, okay? If you had just 2 samples in each coordinate direction, then you would have 4 points. Okay. So what I'm trying to say is, let's say you have a Gaussian distribution, okay? Then in order to say something about the Gaussian, for sure you would need to have multiple points along the x-axis, okay? Maybe you need 10 points, right? I mean, think about plotting, for example, a function. If you wanted to plot a function and you want to have some semblance of that function, you need to evaluate that function on 10 or 20 points in x direction, so that if you connect the points that you have with piecewise linears, it roughly looks like the original function. Okay?
That's usually.
So
you're saying that histograms are an impossibility because we don't have enough points to fill out that space,
yeah,
for example.
For example, right?
I
So I mean, if I wanted to plot just a 1-dimensional function, I need on the order of maybe 10 or 20 points that I can connect somehow, so that the thing that I plot looks roughly like the original function. If I evaluate the function f of x at only 2 points, I'm going to draw a straight line through it, and the likelihood that that straight line is a good representation of the function that I really meant to show is pretty small, right? If I wanted to do this in 2D, with even just 2 points in x and 2 points in y direction, I already end up with 4. I need to evaluate this function at 4 points. And in 64 dimensions, to do this sort of very simplest possible representation of a function, I would need 2 to the 64, about 4 billion points, right? But I don't have 4 billion points, right? So despite my 25 CPU years of work, I don't even have 2 points in each coordinate direction.
So this actually then is like the standard sort of cursive dimensionality argument that you're sampling the sort of same size and it just explodes. So another thing with the cursive dimensionality is that high dimensions Gaussians actually become very heavy-tailed. So is it actually, even if you knew it was Gaussian, would you still be able to approximate a high dimensional Gaussian very well just because it's so very heavy-tailed?
So the Gaussians are sort of easy to compute because all you need to know is the mean value to some reasonable approximation, or maybe just find the point where the gradient of P of K is 0. Okay, so you're finding yourself the maximum of P, right? So you're trying to find, I mean, even if this function P of K is sort of complicated, maybe there's an optimization algorithm that finds you that point where grad P is 0. So you find the point of maximum, that's the mean value of your Gaussian. And the only other thing that you need is a measure of the covariance matrix. And for most problems computing, the covariance matrix is not so difficult. It is much easier to compute the covariance matrix because there's just a curvature at the maximum, right? I mean, I just need to sort of, compute second derivatives in K1 direction and second derivatives in K2 direction, which I can do with just 3 points in each direction. And then I need to work a little bit harder to get the cross derivatives, but it's all not that difficult, right? I can do this somehow. But it's much more difficult to characterize non-Gaussian distributions. So one of the things that I work really hard on to make sure that this benchmark does not actually produce a Gaussian distribution, because it would totally defeat the purpose. Right? I would end up with a benchmark that I spent 25 CPU years on solving, and somebody else comes along and says, "This is Gaussian. I can just compute the mean value, the covariance matrix, and solves the whole problem in 5 minutes." That would be a shame, right? But I made sure that the benchmark does not lead to a Gaussian probability distribution.
Okay, other questions, comments?
Well, I have a comment. Well, thank you first for your talk, Wolfgang. I especially enjoy your overview and the introduction to inverse modeling, as I did not work on this topic myself, but I knew a few of my former colleagues in Jülich worked on it, and they determined material parameters from a fire retardant material called PMMA, and they did their calculations on our supercomputers, and they used a tool that's called SpotPy. And I just wanted to advertise this particular tool, since it's a very, I don't know if you heard about it. It's like a Python package in which you only need to provide a model, and it has a collection of sampling algorithms, and you just need to supply or set your model, pick one of the many algorithms to determine your samples, and then run your program and wait. And then there are analysis tools in the end. And I don't know how efficient that is and how that compares to your work, but it's at least a good resource for more ideas and different sampling algorithms. And
so there's a number of packages like this. There's one by Yusuf Marzouk from MIT, for example, that's called MUQ. There's, I think, one that is part of the Trilinos package. There's many different implementations of sampling algorithms. The question is, how will they perform on difficult problems? And we don't know that. There is no systematic comparison of sampling algorithms for difficult problems. People always compare them on 3-dimensional or 7-dimensional Gaussians, or maybe mixtures of Gaussians. But the real world does not consist of Gaussians. And so I have no trust in somebody saying my algorithm is better than your algorithm because I compared it on a 5-dimensional Gaussian. I think that tells me nothing about how this thing will actually work on a real inverse problem, right? Like for your fire propagation model, for example. So how do you determine whether algorithm B is better than algorithm A? Is, well, you need to have a benchmark. You need to have the correct answer. You need to compare it. That's the point of what I was trying to do with David here, that we come up with a benchmark that allows us to compare these sort of things in a systematic way. Okay, so we're already 13 minutes over time. I think this might be a good time to stop. What do you say Yongcheng?
Yeah, okay. So that was very wonderful talk. Thank you. So yeah, that's it. I will see you next Monday, next Thursday.